So guys, again, half reactions, they're showing us the the exchange of electrons that are happening in a redox, because it's very important for us to keep track of all those because of, laws that we've talked about. Law of conservation of matter. We can't just create things. We've got to keep track of those. So for each redox reaction, we can illustrate two half reactions. Like you already told me, one is going to show just the oxidation that's taking place, and the other one's going to show the reduction that's taking place. So in your notes on page 6, you have a mistake. Your second reaction, I didn't change it around. Okay? They should be like the ones that are on the board for you. So you need to rewrite your second equation in your on page 6. Not only within these individual half reactions are the elements balanced, we've got to make sure that the charge is equal. Now, the charge has got to be equal within both half reactions, because think about it. Are these reactions happening kind of isolated? Redox, like meaning one at a time? No, right? We write them so it looks like they are, but really they're happening what? Simultaneously, which we've already covered that. Redox reactions happen at the same time because one is giving electrons, the other one's taking them in, which allows for that change to happen. So we have to have a balance of charge within our reactions. Now, obviously, this is just a reverse reaction here. You'll see more of what I mean in a few minutes. But if you take a look, guys, the reduction half reaction, the electrons are going to be as a reactant because they're taking them in. They're gaining them. Remember, gain, electrons reduce. So they're going to be a reactant. Where oxidation, it's going to be a product because you're losing electrons. So you see it on the product side right here. Okay, so you've got to think about what electrons are. So if you remember your basic chemistry, what's an electron? It's a negative charge. Okay, so if you're gaining those in, it's going to reduce it down. Where if you're losing it, it's going to take it up higher and become more positive. So, guys, we add the electrons. This is kind of a little trick. Add electrons to the side of the reaction that has a higher total charge. What does that mean, a higher total charge? Higher meaning, yes, more positive. Okay? The side of the reaction, that has the more positive charge, that's where we're going to add the electrons to, so that it combines to lower the charge. So think about it. If we're following that law of conservation of matter, the half reactions follow the law of conservation of mass, where you have the same number of atoms on both sides of the reaction arrow. What are we going to have to do, basically, does that mean? We have to make sure it's balanced, which we've been doing that all along, so you can't forget to do that. I know the homework that we went over yesterday, we kind of skimmed over that just for the sake of practicing the oxidation numbers and identifying redox, but we got to make sure that it's balanced. And then there has to also, guys, be a conservation of charge. So in half reactions, the net charge, meaning the overall charge on the entire reaction, must be the same on both sides. And this last point right here is important. It doesn't necessarily have to add to 0. We think, or we assume, that it automatically has to be at 0. But it just has to be the same charge on both sides. When might be a case where possibly it doesn't add up to 0, if what's present? They have a charge. A polyatomic, guys, is the one that comes to my mind. If you have a polyatomic present, that might be the time where it doesn't add up to 0. Okay? So just be aware that it just has to be equal on both sides, but not necessarily equaled out at 0. Number 1, you always got to start with looking at the oxidation numbers for all the elements of the reaction. Drawing brackets, and what I mean by brackets, guys, you'll see in a second where you kind of draw from one element to the other element of what's being oxidized, the kind of the pairs, kind of similar to how we drew the brackets for conjugate pairs when we did acid-base chemistry. You'll see what I mean. And then you don't have to necessarily do that. It's up to you. We haven't practiced that a lot already. Then we're going to begin to set up the half reactions. We're going to pull out the brackets, bring in element symbols and the charge with you. Set up the reaction with the arrow connecting just like we've done. Here's the trick, though, guys. Diatomics must be pulled out as a pair. Why? Because they exist together as diatomics. They are the only times where you're going to bring the subscript with you. No other elements will have subscripts. So if they have subscripts in a formula, how are we going to fix that? What are we going to use to make sure it's balanced out? coefficients like we've done all year long. So think back to your net ionic equations. None of those had subscripts. This case, the only time we will is when we have diatomics. All right, when we have, I could not think of that for the life of me. I was going to say binary. I was going to all this. It's I was going to say poly. Diatomics. 2. Brinkelhoff. That's what I'm getting at. Why am I yelling? I don't know. All right. Trying to drive it home in my head. That's why I'm yelling. Number 4, reactions, guys, involving diatomic elements only. Balance your mass first to make sure you have the same number of elements on each side. And then the last step is to make sure you balance the charge in each half reaction, where we're going to insert the appropriate amount of electrons to attain that conservation of charge. Remember, electrons are negative, guys, so the net charges on each side should be equal after you add electrons. That's a new piece, okay, that you guys started to see in the homework sheet the other day. Okay, so we're going to add those electrons to balance out the charge. So let's take a look. Here's what I mean with the brackets. Match up the ones that pair together, all right, that change their oxidation state. So magnesium, let's go through and assign those. What's the charge on magnesium? 0. Zinc is 2. Either way. Chlorine's going to be? You got to give me a sign too. Oh, you said negative. I didn't hear you. -1. Magnesium's going to be? 2 plus. Chlorine's going to be? 1 minus. And then zinc is going to be? So which element, guys, is not taking part in this redox? Chlorine. So we can get rid of that and not worry about it. So this is what the brackets are. If it helps you, great. If you don't need it because we've done a lot of practice, that's fine as well. So now, identify which one's oxidizing. Oxidizing, you're doing what with your electrons? Ooh, I hear both. Oh, oxidation. How do we remember oxidation? Leo. Lose electrons. Which element loses it? It already says it for us. Magnesium. So now, it doesn't matter, guys, what order you put these on the side with the electrons. I'm going to usually typically fill in my element first, then I'll worry about the electrons after. So my new oxidation state for magnesium is 2 plus. Well, we've got to balance out the charge. We have 0 on the left side of our reactant. Okay? We've got to make sure we have a total cumulative charge of 0 on the product side, the right side. How do I balance that out? 2 electrons is what we're going to need. Okay? So that +2 and that -2 are going to balance out, so we have a conservation of our charge taking place.
Yeah, I thought that was a Z. I was like,
No, that's why I make my Z's like this, just like my 7s. So, anyway.
Would we add those electrons to the right side?
What do you mean to the right side?
Or to the left? Like added to the left side of the reactor?
You mean put more over here?
No, up on the top.
No, we're not doing anything with it. We're writing just the half reactions. You're not putting that in the main reaction. That's the half reaction, guys. That is the oxidation half reaction right there. So now reduction. What are we doing with reduction? What's the saying? Gur. Gain electrons. So if you're gaining them, guys, they are like a reactant. So now over here is going to be our new species, zinc 0. Well, how did it go from +2 to 0? It gained 2 electrons. Okay? Now, if we were to put both of these half reactions together to show kind of similarly to our net equation, or net ionic equation, we did those net ionics, we could put it all together so we would be something like magnesium 0 plus zinc ion plus 2 electrons would yield, and it would just be all of our products. Mg2 plus 2 electrons plus zinc 0. You do not have to write that in there, but that's showing the full redox of what's actually taking place in our equation. Okay? It's balanced out on both sides with how many elements we have as well as the electrons, so the charge remains. Okay? So take it piece by piece, and just remember, Leo the lion says, grr. Okay, I want you guys to try example number 2 in your notes. Assign our oxidation numbers. Easy. 0 and 0 because they're by themselves. Okay, what about in our compound? Which one has the negative charge? Iodine. It's the more electronegative element. The charge then on mercury has to be what? +1, so that they're balanced out because there's no charge there. So now, which substance, which species, guys, is getting oxidized? Question or answer? Question. What do you think?
Yeah.
Absolutely. I know. So that was a point I was going to get to in a second. So why don't we go back, guys? While we're doing this reaction, balance it. That's, again, you guys are in that habit, so continue with that. How do we balance this equation? 2, 1, 2, okay? That will follow us because we've got to make sure that we have our charges balanced out as well as our masses. So oxidation half reaction. Which substance is getting oxidized? Yeah, Hg. It's not hydrogen, it's mercury. So Hg, how many of those did we have?
1, 2.
Okay. Now, you can kind of wait and balance it at the end, guys, if you wanted to. Okay. But I would continue along with it from what we had up above. So we have 2 mercury, 2 moles of that. And we're going to produce 2 mercuries with what's the new charge here? +1. Now, what's our total positive charge that we have with 2 moles of the mercury, guys?
+2.
It's a +2. So how many electrons are we going to need to balance that out?
2.
2 electrons to balance that out. Now, half reaction of the reduction. It's got to be iodine. It's I2. Why can it be I2? Because it's a diatomic, part of Brinkelhoff, okay? Now, reduction means you're gaining the electrons. So which side of the electron is going to be on? On the left, okay? How many? 2, because we have 2 atoms of iodine that are going to be balanced out, and then we have 2 iodine with our negative charge right there. Okay? So it's pieces that we've been doing all year long. Now we're just adding a new component in here, guys, with the electrons. Okay? Balancing out the charge, where we didn't necessarily do that with those net ionics that we talked about before, because they weren't redox, they weren't changing. All right, go ahead and try number 3. If you take a look up here, guys, oxidation states. I'm going to keep this as a polyatomic. It's -1. This is +1. Copper becomes +2. This still stays as -1. Silver becomes 0. How do I balance this equation? 1, 2, 1, 2. Okay. Which substance is getting oxidized? Copper. Okay, so copper is there, and it becomes Cu2+. How many electrons will we need? 2 electrons. So now if we look at the reduction half reaction, guys, if we waited to balance out until the end, okay, then we can multiply like it's showing here. But since we balanced it at the beginning, because we're used to that, we're kind of taking care of that work and making sure things are balanced all along the way. So what substance is being reduced? Silver, okay, much like we did in the lab. Or attempted to do. Well, we did. It just didn't coat like we wanted it to. So we got +1. Now, how many silver ions did I start with? 2, right? Because we balanced it. So it'd be 2 Ag+. How many electrons will then be needed? 2 electrons. And then it's going to end up with 2 moles of silver. Now, guys, notice, with both half reactions, you should have the same number of electrons. One's going to be on the product side, the other's going to be on the reactant side. Why do you think that is? Besides just, that it's the conservation of charge. But what's happening with redox? Absolutely, that's what redox is, guys. One is giving them up, which again, the oxidizing agent is allowing for oxidation to happen by reducing, by taking in the electrons that the oxidizing piece is giving up, that they're losing them. So we're going from one element to another, so this should make sense that on either side of the reaction you have the same number of electrons, okay? If it's ever different, you know you've done something wrong, all right? Questions?
Where are you getting the 2 electrons? Where do you get the number?
Like, you mean I'm just, like, it seems like we're just picking them out of nowhere? It's because we're looking at the charge here that has to balance it out, right? So we had a 0 total on the left side of our reactant, or of our reaction, okay? So then this becomes +2 based on the overall reaction. We know that it becomes +2, so that means, it's losing 2 electrons. When you take the 2 negative charges plus the +2, that equals that 0 that we had to begin with, okay? And really, This copper, if you think about its electron configuration, it let go of its two outermost, and then they didn't just stay there. Silver took them in because it was being reduced. That's where we get this 2 plus that comes along magically to just, balance it out, but not magically. All right? Good questions. Any other questions? Now, Table J, guys, this is a review. We've talked about this, but now we're going to apply it again and talk about spontaneity. So, general rule, guys, elements that are where on this table, higher on, they are what in terms of reactive? More reactive. We've talked about this. It's been a while since we looked at it. The big thing, guys, we want to think about now in terms of spontaneity, will the reaction happen or will it not happen? Okay. If the reaction occurs, if it's spontaneous, that means no extra energy's been added. It's actually just going to happen all on its own. Okay? That's where if something is higher up that's trying to come in and kick out the piece that's lower in activity, all right, it's spontaneous. But if it's non-spontaneous, meaning something is lower, let's say iron here is trying to kick out manganese, you would have to add energy into the system to actually make it work. So I want you guys to go through right here. All right, complete the following equations by writing in the products form if it takes place, or write no reaction. Okay? Should be quick and easy. Number 2, zinc trying to replace barium. Will that take place? No, so there's no reaction, meaning when we say no reaction, guys, it's not a spontaneous one. We could get that reaction to go if we added lots of energy to it, but it's not naturally going to take place. Calcium kicking out chromium 2?
Yes.
Yes, it will. So CaF2 plus chromium. Example number 4, manganese trying to kick out nickel.
Yes.
Yes.
How do we know the charge on manganese?
Great question. Okay, so with those transition metals, guys, if they don't tell you, assume it's the first oxidation number that they give you. So that would be +2 here. All right. But also, you could also think about it in terms of, all right, what's nickel's charge here? Because if it's a redox reaction, okay, it would kind of keep that balance a little bit. But assume that it's just going to that most common state there. If I see anything else different as I'm going through looking stuff, I will let you guys know, and we'll go back and correct that. Next one, iron and magnesium. No reaction. And number 6, cobalt trying to kick out lead.
Yes.
Yep, so it's going to be cobalt. Again, cobalt 2 chloride is what we'll go with, plus lead. Any questions, guys?